We do not yet have Charlie Bolden here, so we will press ahead with our normal activities. And just to kind of give you a gauge, flexibility is the key to a flexible path, right? So we will be flexible. So when and if Charlie shows up while we're briefing, we'll go ahead and finish that particular brief that we're in order to have continuity. But then we'll go ahead and turn it over to him to address the group. A couple of administrative announcements. I think you got to see firsthand a little glimpse into some of the mystique of the Blue Sky Innovative process. This is the first time we've tried it in this large of a group format, and I'm very pleased to say that after floating around and visiting each of the groups, you should all be applauded. I think it was very rich and dynamic. Some were more robust than others. Adding a little competition is always good. Of course, we did have a winner. Doug Craig's ConOps group was probably the most prolific, so kudos. But indeed, this is a foreshadowing of tomorrow. Certainly, we went through the storming, forming, norming, and performing, all the little ings. Some groups didn't quite get all the way through that, but at least today, we will now have more time tomorrow in each of the sub-breakout sessions, more time not only to dialogue and deliberate, but we'll also have more time to prep for and do the outbriefs. This was all about getting a very time-constrained, focused lightning round of brainstorm inputs all on the same topic. So kudos to everybody and great job thus far. So without further ado, we're going to walk through. Each one of these study leads is going to walk through and in 10 minutes give you a summary overview of the key takeaways out of their particular group. And so we'll keep it strictly limited to the 10 minutes. This is kind of a one-way push of information because we have 6 groups, 10 minutes a pop, 1 hour. And so without further ado, Doug Craig. Actually, I'll walk through each group and say the lead's name and what group or what they were focusing on. So first off, in the ConOps or concept of operations, we had Doug Craig. Then we had Planetary Defense, which we had Lindley Johnson leading that. Then we had Gail Allen, who led the policy subgroup. Next up, we had technology, which was led by Barbara Wilson. And then we had Chris Culbert doing synergies. And finally, we had the dynamic duo of Sandy Magnus and Jay Jenkins doing precursors. So with that, I'll turn it over to Doug.
All right, thank you, John. First off, just wanted to say that, as John said, we did come up with a lot of ideas, and kudos to the scribes, both Lauren and Dan Masnick, for being able to try to keep up with us. It also made consolidating the points a little bit more difficult, but we got through it. So if we can have the next chart. So what we did is, and you're going to see that we focused a lot on the deep space exploration. We had 13 different objectives there, then the science, and then planetary defense, and then we came up with some others. And one of the things that we noticed this morning, and once we went through all of the different objectives, thanks. Yeah. That there are a lot of overlapping objectives and activities. And so we ended up seeing common themes throughout. All right, so the deep space capabilities, the objectives that we came up with, actually they all you could categorize them in 3 different areas: the operations, human research, and hardware systems. For operations, looking at autonomous operations, once you get farther and farther away with the time delay of the communications, the crew needs to be more and more autonomous. Also, the degraded communications. One of the ideas that was talked about was the in-flight training, basically using the time out to train for your NEO missions. This is going to be important, especially if you miss a launch opportunity for one NEO and you have a different type of NEO that you're going to. So that was a nugget there. And then also human and robotic operations, how are you going to do that so you can train on the way once you're there? And also how do you categorize the different functionalities between humans and robotics? For human research, physiological, radiation research, also psychological, and the partial gravity. How can you survive in that? Hardware systems, we had a lot of inputs there, as you can imagine. Basically, it kind of folded up into long-duration systems. This is a great way to test for future missions, things like ECLS, life support systems, all of your systems' reliability and maintainability. If you're going to go out for 6 months to a year and you don't have an easy way back, you're going to have some real reliable systems, and this is a good stepping stone for that. The activities, talking about practice in NEO operations, actually you could do that in LEO, but also en route. Also practice in the long-duration flight. Sampling, handling, and curation, radiation mitigation. Also the testing of the systems. You're testing the high ISP propulsion systems, as well as deep space comm, ISRU, and like I said, the autonomous operations there. For the target characteristics, looking at kind of a medium to large, not rapidly rotating, and looking at high water content for the NEO. The scientific research looked to characterize the physical parameters, the composition and resources of it. Some of the activities would be subsurface access, the drilling, core sampling, also looking at the structure using seismic activities or seismic sensors. Also doing surface sampling. How do you go about doing that? Robotically versus and humans. Also looked at, do you take small samples, or maybe there's some bulk sampling activities you can do, and then what you would do on the way back is to triage. So that was one of the things that came out, one of the nuggets. Deploying scientific instruments for ongoing operations. So once you're there, you leave the payload there, and it would continue on operating. You could also use that for public engagement for participatory exploration as well. The target characteristics, what we heard this morning was that all of them are scientifically interesting because we have such a small N number of information on the NEOs that we have. So the planetary defense, the objectives that we had, basically looking at identifying and characterizing the threats, looking at the composition, looking at the size, porosity, and then looking at how do you mitigate the threats, and validate that you have mitigated the threats. Some of the activities that we were looking at is demonstrating the mitigation techniques. If you're looking at, as we saw, low impulse pushing or high impulse, or depositing a physics package or a bomb to detonate, trying to figure out what are the best operations to do that. The other activity was to identify all threats. That was one of the themes that came out of this morning that everyone seemed to resonate with, is the basically doing surveys for the NEOs. And then a better understanding of the human operations for NEOs. And so this is one of where the more familiar we are with operating on near-Earth objects, the better we're going to be in the future if we have a potentially hazardous object that we need to deal with. We'll be in a lot better position to work with that. The target characteristics, we were looking at small ones to practice on, so and ones that are in non-threatening orbits. You don't want to practice your mitigation technique on one and then have an accident and make it even more potentially hazardous. So practice on some smaller ones, and then once you get that under your belt and you feel a lot more confident in handling those, then you can go to the larger ones, the potentially hazardous objects, the ones in the orbits that are potentially hazardous, as well as ones that are greater than 30 meters. And that's it.
Thanks very much. Super. And below time. Great. Lindley.
Okay, I feel like a bad penny. I keep coming back up here. Okay, let's see. I guess I can control the clicker here. Or am I not loaded yet? We had a lot of interesting discussions within the Planetary Defense Group. We've spent quite a bit of time, numerous years, in talking about what would we do if an object showed up that we had to do something about. And, our thinking is that we have to do something about it robotically because that's the only way you'll be able to get to it in time to do anything. So it's really, we have to open up our thought process a little bit to think about what humans can do, a human mission can do for us at an NEO. There is a school of thought in the planetary defense community that if you ask them what the role of humans for planetary defense is, they will respond, ballast for the gravity tractor. So anyway, we took a while wrestling with that for a while, so we didn't have a chance to divide things up into the 4 themes here, or 3 themes. We're all about planetary defense. But I think you'll see that these things can be subdivided that way. We've got quite an overlap with what we saw with the operations concept. Let's see. So nothing there, nothing there. Okay, now you probably can't read these. Wish they had divided them up a little bit more because I can't read them either from here. Okay. So objectives. Well, the big objective is characterizing all the properties of the NEO that you're going to try to learn as much about these things as we can, because there's a lot that we don't know. And then determine effectiveness of different deflection techniques, be it gravity tractor and some of the more exotic things we talked about, like laser ablation or just simply painting in a different color and let solar energy do the rest. But along those lines, examine various ways of attaching devices to the object, be it for applying some kind of thrust or for mining the asteroid and doing a mass driver. Another big objective is verification of remote sensing. In other words, getting ground truth, actually going, having observations of an NEO and then going there to see what it really looks like, and so that you can then do the comparison, cross comparison, so that new objects found, we then can better characterize them remotely. Sample return, sample return, sample return. It's a big one for both planetary defense and science, we know. Some of the other benefits I think we would get, though, from a rather large deep space operation is the simulation and experience in a multinational, multi-agency planetary defense campaign. It will take certainly more than one mission should we have to deal with a threatening object. And planning the operation and coordination of such an operation. Public buy-in, public attention, more public attention to the planetary defense issues and the mission. Certainly involvement of the international community in developing planetary defense techniques and being involved in the overall effort and planning for those kinds of things. And then similar to concept of operations, verifying and exercising autonomous proximity operations. So some of the activities, specific activities you would do to implement these, achieve these objectives: collect samples, observe, examine the result of various deflection techniques, be they gravity tractor or laser ablation or other types, even observing, hopefully from standing off a ways, a small kinetic impactor. Testing of terminal phase and guidance and control technologies. Operation of avatars to explore parts of the NEO or to do operations, remote operations on the NEOs. Implanting sensors, seismic sensors especially, and the stimulators for those sensors. Measure and examine the overall NEO environment, things that need to be dealt with. Drilling to determine in more detail and more depth, I was about to say, the characteristics of an NEO, and as I've mentioned, observe the response of laser and other focus techniques. Characteristics of the target we would want to go to. Well, first of all, we think we need to do a lot more as far as survey to get a complete target selection catalog, so we know better what is the overall categories collection of these objects, so that we can better select what targets would be the most effective for us to go to. Certainly interested in targets that really do pose a potential impact hazard, and of course the more common impact hazard is going to come from the smaller objects, so going to those and understanding their characteristics and dynamics better would be a top priority. But we really think there needs to be a queue of targets over a course of several years for the human mission, both for hopefully going to multiple missions, going to these targets, but there are inevitable delays, and when you're dealing with planetary windows, if you're not able to get off in the 2 or 3 weeks, or sometimes as much as a month, if you're not able to get off in that window, you've got to move on to the next target. So you've got to have a slate of targets in mind. There's two schools of thought about these next two things. One is that, well, at least initially, we should choose relatively simple targets that have simple characteristics and simple dynamics, in a spherical shape, slow spinners, something that's not going to be too much of a safety issue. But there's another school that says that, well, you're not going to be able to choose which NEO is going to be an impact threat to the Earth. Somebody or some other power chose that a long time ago. So we're not going to know what we're going to be dealing with, so that we really should be developing the capabilities against the more challenging types of objects, so that we push the envelope. So we should be acquiring the technologies and the capabilities to go to longer duration missions using SEP or some other long-term propulsion, things that push our capabilities and our abilities to respond to an impact threat should it, God forbid, ever occur. And I think that should be it. Yep, thank you.
Ladies and gentlemen, it's my distinct honor to introduce the Honorable Charlie Bolden, the Administrator of NASA. He told me briefly on his way in, he says he's really Neo, man, and he's coming to check our work. So with that.
Thank you. I know you're about good stuff, so I will not take very much time. I wanted to come over and welcome you. I had hoped to be able to do that this morning, and I wasn't able to, and I want to apologize for not being able to spend more time with you. What you're doing is really important stuff. And I know I'm preaching to the choir in most cases, I think. But in case there are some unbelievers in the audience, this is not science fiction. John Holdren, everybody know who John Holdren is? The President's Science Advisor, head of OSTP. He loves to tell stories about NASA because at least once a week he goes into the cabinet room and they meet with the President. And he said the President has this habit of saying, tell me something I don't know before the session ends. And he goes around to the cabinet secretaries and to the other people, and he said most of them on most days say, I pass. But he said he has never passed because he has generally had something from one of his science and technology agencies, but mostly from NASA. And he says he remembers the morning that he had the Jupiter image from Hubble of, was it Shoemaker-Levy? No? Which one? Tell me, help me here. Yeah. Unknown. Aha. We don't know. That's even better. That helps my story even better. I think you can see where I'm going with this story, but he pulls out this big image from Hubble of Jupiter with this big black hole. And he passed it around, and everybody looked kind of, and he said, Mr. President, this is an image that was taken by Hubble, and it's a particle of some nature that we did not know, we did not forecast, and it impacted the planet Jupiter. And you see the little black spot there. That is several Earths in diameter. And he said the room fell silent. And he said the president got it, and most other people sitting around the table, I cannot attest, I wasn't there. And most other people sitting around the table got it. And I think, if you look at the national space policy, there are several things that I like to tell people are really important in there. One of them is the degree to which the president has emphasized the importance of international cooperation and going forward. And the other one is the degree of importance that they put on what we all call planetary defense. The fact that this is not science fiction. That we're talking about things, some known and mostly unknown. The Congress realizes it because they have directed us over a period of years to identify and characterize. 90% of the objects, I guess 140 meters seems to be the dividing point or something like that. At one time it was everything bigger than that, and now it's everything below that. And what I have to go tell them is I can't do that. I can help and I can get close, but I don't have the capability of doing that right now. And so we, NASA, have got to become innovative, and we've got to find ways to go do that if that's what you really want us to do. And it is important because, one of these days, one of those stray pieces that we just didn't see coming because we hadn't characterized everything and we hadn't identified it, could head this way. And we would like to feel comfortable that we at least stand a fighting chance. So I'm glad to see all of you here. I understand, I can tell by the uniforms that there's some non-NASA people here, although some NASA people wear uniforms. But I hope there are a number of you here from academia, and that if you're not if you're not intimately involved in this right now, that you will go back and talk to your students, because this is exciting to them. And I think you all know that it will help you draw young people to your campuses if they know that there is research going on in this field, because this is what keeps the dinosaurs, we are the dinosaurs, by the way. This is what keeps the dinosaurs from becoming extinct a second time. So, I thank you very much for giving us the time, for taking time out of for some of you, your busy summer schedules where it was the only time you could get away. So I really do appreciate your being here. It's important that you're here. Go back home wherever that happens to be, even if it's here in town, and tell people that we're serious about this. This is not just an exercise, and it's not science fiction. It's about real stuff. And it's about things that we really can make a difference on the future of humanity if we take it seriously and we apply ourselves. Cost is not an independent variable, okay? Cost is a very important, not very variable. So we have got to be innovative in the ways that we find our ability to do the kinds of things that you all are going to talk about, have been talking about today, and will continue to talk about the rest of the day and into tomorrow. So I've taken enough of your time, but thanks so much for coming. Some of you communicate with me because when I say things like, it was a fragment of comet Shoemaker-Levy, you all have gotten in the habit now of either reading my speeches or you're at a speech and you send me a note that says, you were talking about the asteroids and this kind of, that wasn't quite right. I appreciate that because I usually make some error in statement every time I go out, and the more you all feed me, then the more accurate I will become, and the more I will learn about what's important to you. So thanks very much again, but thank you.
And now, fittingly, to follow the administrator, and thank you very much for that excellent set of words of wisdom, we have Dr. Gail Allen talking policy.
Well, I wanted to start out by mentioning the fact that if you look at the makeup of the team that we're working with, it's no surprise that no one was shy, and secondly, there was tremendous richness of information exchanged. But I started getting worried toward the end when one table started referring to the other table as the parking lot, because they thought their ideas were so much better than anybody else's. So, only in jest. Okay, so we had a pretty prolific amount of ideas, as you can see, for the themes for the deep space. We had 25. Planetary defense, we had 13. And for economic expansion, we had 5. And some of the general observations were there are obviously multiple approaches for why we want to go to humans to NEO, different directions, different reasons. And what we all agree to is we need to take a thoughtful approach on how we manage this and how we plan it so that we make sure we have a maximum investment. As you heard earlier today, it isn't inexpensive to do it. And some of the other challenges are that there are so many asteroids out there. A lot of them are not available, but then by the same token, they're so different that when you go to one, one size doesn't fit all. So for deep space capabilities, the objectives and key observations, we decided that the mission should contribute to planetary defense and economic expansion. It should demonstrate the ability for extended operations in deep space, specifically in hardware demonstrations, software reliability, and ability to do repairs. Also build in the flexibility and the ability to respond in real time to new information. We're not going to be able to plan for everything that could possibly happen. We have to be flexible enough, and our crew has to be educated enough for us to be able to deal with things as they come in, new information and how we want to assess it, or even in other situations. And also, we need to determine about the dust mitigation techniques and develop them. For the activities, we need to ensure an open communication between crew and folks on the ground, make sure that that line of communication is open and we have redundancy there, develop robotic installation techniques, develop adequate radiation shielding, mitigate reactive chemistry, and we didn't address the target target characteristics. For scientific research, the objectives would be to characterize resource-rich targets, structural stability and chemistry, identify human factors, risks of extended missions. Obviously, for these types of missions, we're going to have to plan in much more detail and be prepared for these extended missions. We're not going to be 2 or 3 days from home. We need to learn more about the beginning of the solar system. For activities, we'd like to see safely remove a core drill sample from multiple depths of the asteroid, leave a scientific network for tracking, seismic monitoring, and take multiple samples across NEO population. And that fits into where we know that one NEO, collecting data and characterizing one NEO robotically is not going to give us the answers we're going to need for a human mission, especially in the fact that as the next one, the target characteristic would be, some of the discussion we had was that you may be able to target a NEO robotically and characterize it, but then are you going to wait 15 years to be able to for the next opportunity for a human mission to occur on the same NEO? So how do we address and how you deal with the differences across the characteristics of all the NEOs and make sure that we've got preparation in place for human missions that can occur safely? For planetary defense, objectives were for protection, and there was a lot of discussion on defense, and everyone seemed to think collectively that defense means constantly defending. So we wanted to put protection because part of the mitigation is defending in a way, but is also being a little more proactive and not reactive, that seemed to be the trend on the defense discussion. Plus the economic driver, we should have those two as the level 1 objectives for a planetary defense theme, and be able to answer the questions, be able to characterize enough of the NEO population, especially the ones that are the nearest to us, to be able to develop a reliable and concrete risk mitigation plan and make the decisions around that. For activities, obviously test deflection techniques, development in international working groups on threat mitigation, safely remove a core drill sample, leave a scientific network, and then the other is take multiple samples across the NEO population so that you can get that broad brush of characteristics that might be needed. For target characteristics, accessibility obviously is one of those. We need to look at what's the reasonable approach to take, and the representative of a population of interest, scientific interests, commercially useful, and are potentially hazardous. And address all of those, or each of those, or at least prioritize them so that we know that we're investing these high-dollar missions onto activities that will give us the biggest return on our investment. The last one was economic expansion and in-situ resource utilization. The objective is to identify very valuable materials, and the activities would be develop means for gathering resources from NEOs, develop a NEO resource map. That's especially important if we're looking for economic growth or opportunities in that arena, and possibly grappling and bringing a portion of an asteroid back close to Earth and Moon so we can maybe harvest it that way. I think that's it. Thank you.
Thank you. Next up, Barbara Wilson with technology.
Where's the clicker? Right there. That's the right advance. There's a laser pointer.
Okay, this was the group that's going to be looking tomorrow at capabilities and technologies, and that's by and large a lot of the background of the folks at the table. Are we up? We go to the next one. If not, does it need to be? Okay, finally. I clicked. Okay. Okay, so the charts that we have here don't begin to do justice to the richness of the discussion at the table, I have to admit, but we did have a predominance of objectives identified in the deep space capabilities arena. We also had an interesting discussion on the whole question of what is special about humans that makes it, that means that you can do special things or do unique things when you have humans present, which wasn't captured really by this format, but included things such as the ability for humans to discover new things, to be good at pattern recognition and learn new things that you didn't go with the intention of learning when you launched. And also, of course, the fact that the humans being present means that the humans are the experiment, and so you also have to learn things about how humans can survive in deep space. In terms of the deep space capabilities, the general overarching idea is that you're developing and testing and demonstrating capabilities that you need for long duration deep space missions, some of which you might need for this mission, but some of which would be things that you would be testing for future missions. So in terms of shaking down and bringing down risks for future missions, and specifically looking at the idea that you are out there not getting supplies, not getting support for repair, not having a medical facility nearby, et cetera. So looking at high reliability, low maintenance, and long life approaches. This includes in life support, but also power and propulsion and all hardware systems in the loop, both for this mission because you are out there without resupply and support, and also, of course, for being out there even longer in the future. There's also the understanding of resources available for utilization downstream for future missions, as well as for economic and commercial activities. In the scientific arena, there's sort of an overarching thought there in terms of developing an understanding of solar system formation and evolution, and with a big focus on sample return. And that includes a number of activities, such as including the extraction, the coring or drilling from subsurface, and bringing a sample out and sustaining it on the way back, for that matter, too, encapsulating and sustaining it in the pristine condition you need to be able to analyze it when it comes back. The intelligence selection is another aspect of having humans present, and to understand then, to provide this as a context for understanding the meteorite collections that we currently have on Earth. In the planetary defense area, the idea here is that you are providing ground truth for the remote sensing and modeling that we may already have developed and are continuing to develop in order to define the diversity and characteristics of the NEO population. We looked at the idea of needing to emplace retroreflectors or other capabilities for orbit determination or for subsequent experiments that would occur after the humans departed. And to characterize while you're there things obviously such as mass, internal structure, rotation rate, et cetera. And what didn't make the chart here, we have test deflection methods, but we had a much more lengthy discussion of aspects of what you might want to do to test and validate deflection methods that you could practice on while humans were present. And I guess that is the end. We also did, I thought I had one more. Is it not? There. Oh, in the other category, we didn't get everything down here on the chart, but first of all, there was the question of just rekindling this culture of real exploration and discovery, both for inspirational purposes as well as guiding us into more extensive discovery out in deep space. And we also had other thoughts about the economic expansion idea that didn't make it onto the chart, and things we wanted to do associated with both measuring what is there and also learning to do things at a low cost to enable future commercial-based activities.
Okay, so let me start by thanking the facilitators and the scribes who worked really hard during all this to gather data. This was running at a lightning pace. Kathy Larini, Brian Wilcox, Ageetha, and Neil did a great job. Those of us who've done blue skies, this felt really fast, John. We tend to have a little more time to work these through in the blue sky sessions, but I think there was some good results, and it was certainly very interesting, and the teams brought out an awful lot of enormously useful, interesting data. I'm going to try not to, we're now 5 groups in, so I'm not going to repeat the same thing you've heard 4 times already. I'm going to try and hit the highlights of things that we thought were a little different. Not to disservice the team, which, as you can see, produced an awful lot of data. In fact, John, I think Doug's group had the smallest number I've seen so far. Anyway, from the standpoint of deep space capabilities, one of the themes I think we talked some about that might be a little different than what we heard so far is something along the lines of sustaining your capabilities. Don't treat this as a one-shot mission. You need to have a set of capabilities that represent a sustainable architecture or infrastructure for long-term use. And that would play key elements in your discussion about when you go, not so much where you go, but when you go and the capabilities you need to enable you to get there. Certainly the demonstration of technologies you need for deep space exploration in general. And we listed some of the key ones: radiation shielding, some of the life support capabilities, power, ISRU, microgravity, all of those things that enable humans to not just go to a NEO, but in the context of a sustainable architecture, enable you to do much more in the long run, are important and very useful. We had a healthy discussion about the role of political objectives or political agendas in these kinds of discussions. And the fact that to some extent you make these choices not because they represent a specific technical need, but because you're given a political framework that you have to fulfill. That doesn't alleviate you from defining and flying technical missions that are credible and capable, but it does put a little different context to some of the decisions you might make. Our team also identified the importance of potential commercial or economic activities. We also talked some about the psychosocial interactions, representing these as long-duration missions, and in fact just the first in what might be a series of long-duration activities with teams of humans for long spans of times. Understanding some of those psychosocial interactions and the teamworks and the interactions of the crew over time is something that's important. Let me look for some of the other, somebody else I think mentioned participatory exploration, the opportunity to keep people interested and engaged in what you're doing. Some of the activities that humans might do under the context of exploration, looking at and understanding the local decision making to ensure that you not only do your technologies work the way you want them to, and then you demonstrate them effectively, and you trigger and enable the kind of autonomous capabilities you need, but that you understand where they didn't work well. And you can learn from that for your future mission capabilities for the kinds of technologies and capabilities you need. Let's see. Vehicle inspection and maintenance. I don't think I heard anybody else mention that. Well, again, these are long-duration activities. This is the start of our ability to deploy humans into environments where they don't get a lot of support and a lot of infrastructure behind them. They're going to be on for very long spans of time. We need to give some thought to how we not only keep the humans alive, but we keep their infrastructure, their vehicles and their systems alive as well. These are you know, a little longer than moon missions, and forgetting for a moment the Neo Prime. I like that, Clive. But the longer, harder to reach Neos give us the opportunity where we still have the opportunity to bring people home potentially with some failures, and some thought needs to be given to how we do that. And when we talked about target characterization, understanding the opportunities for resource characterization would be something that's very worthwhile. We had a long discussion about science objectives. Sample returns showed up in our discussions as well. But beyond the samples themselves, some understanding of the space environment and assessing what that meant, both on the way there and at the NEO itself. And then providing all that information back into a larger picture context, global, or really even the solar system context, and understanding how those things tell you useful information for future missions and other activities. We talked quite a bit about the role of the humans in these activities, essentially bringing human cognition and human intelligence to these activities to help guide the science that you want to do. The science is still done largely with the instruments, but the human bring the opportunity for you to get a more flexible discussion of how you deploy and utilize those capabilities while you're there. And again, target characteristics shows up in some of the same things you've seen from the others, not too much spin, of a reasonably interesting size, volatile or rich, or telling you things about the early solar system. The planetary events, some of the orbital dynamics considerations gets to be an interesting discussion here. And in particular, the human missions might give you the opportunity to get a more rich set of data, both before you perform a mitigation attempt and then after you've done it from a local environment. Some of those observations will have to be done over a long span of time, probably from Earth still. But the opportunity to utilize the humans in situ as a way of gathering some of that data right away could be very valuable. Obviously, some of the same kinds of things you heard from the other teams, the experiments for deflecting NEOs, the ability to correlate what you learn with the humans there for what we've learned from remote activities is very important. Before and after measurements of kinetic data, looking at the internal structure, I think some of the other teams have measured that. The humans give us the opportunity, and these kinds of missions give us the opportunity to learn things about internal structures of the NEOs that might be very important for understanding the nature of threats from future NEOs, or really PHOs, PHAs, the one that are approaching. It may turn out that some types of them are less dangerous than others. Using these kinds of missions, the opportunity to help educate the public. I think one of the people mentioned that already. The opportunity to teach them why this is important and why they should care about this is something very valuable. And I think we didn't capture anything else. Okay, that hits ours.
Okay, so precursor group one are a bunch of people that really, really want to send robots. So we had a lot of discussions clearly about what our human objectives should. You're right, Barbara, where is it at? Yeah, I'm on the right side, but where am I pointing? There we go. Okay. So in terms of deep space capabilities, again, we really wanted to stress that this is human missions. It's not technology development. This is what human beings will be doing while we're there. And what we're talking about is demonstrating the human tolerance for extended missions. This is a stepping stone toward further and further exploration of deep space, a stepping stone toward human exploration of Mars. Determining the potential resource utilization characteristics, characterizing these NEOs for the potential of sustaining further exploration, and demonstrating teleoperation. And it's not so much the Earth to the location as the relatively close proximity, sitting in the hab while hoppers are trying to hang on to the NEO ahead of human beings attempting to do so, but operating it from local proximity. So the types of activities, sampling, which clearly is a predominant activity that goes across all the themes, constructing the infrastructure, and that's the overall infrastructure of exploration, using the NEO activities in order to develop the additional systems for sustained exploration. demonstrating autonomy and accounting for light time delays. As they get longer and longer and longer, it's almost impossible to have a conversation with a 10-second delay between sentences. We tried. Demoing tools for use in deep space. The target characteristics, basically water-rich targets were of interest, things that are larger, things that have short mission times, and things that have slow rotations. Scientific research theme, again, top-level scientific, it comes down to the human-assisted science activities to help determine the history and origin of NEOs, composition and structure. Sample returns is ubiquitously there. Understanding the frangibility and the behavior of the body in microgravity. If you take your glove and you brush across it, how long does the dust stay, pose itself to be a threat. So what type of activities? Conducting in situ spectrometry, they did that to me deliberately. In situ spectroscopy, emplacement of long-term observatory perhaps, intelligent human selection, sample selection and placement of geophysical instruments. And that was one of the key things, is that we do this with robotics. Why do we need a human being? Well, it's the human being providing that value-added component to be able to intelligently select sample locations in order to select sample locations that are not necessarily easy to get to autonomously. Being able to emplace things for the long run was really the core theme that we developed there. And again, target characteristics, larger water risk, rubble piles, binary if possible was mentioned. In terms of planetary defense, key observations, number one, first do no harm. Don't make a bad situation worse. Don't take a non-threatening asteroid and turn it into a hazardous course. That's number one objective. Beyond that, objectives could be the determine or demo the ability to modify the delta V of the asteroid, to determine its internal structure and composition, or to inform future mitigation technologies. Understanding, again, its fragility, its frangibility, its breakup potential. And then in terms of the activities, in placing the sensors, in placing delta V devices in order to meet these objectives, and to demonstrate the mitigation concepts, which could involve using a kinetic impactor, in placing some type of detonation device or something of that nature. And this target characteristics, generally picking a NEO that would be most representative of the most statistically likely threat. And that's what we had.
Well, I'm from the representing the second precursor group, and I guess it's both a good and a bad thing to be last. Bad because a lot of things have already been said that we have to present. Good because it'll be really quick, and you guys will love it, and we'll be done. So George and Mike did a great job facilitating, and with Sasha and Katrina's help, we were able to come up with a couple of slides. A lot of lively discussion. We had a lot of the same ideas being repeated over and over again, and what we did was, instead of breaking them up, we put planetary defense and science sort of in the same category and kept it very big picture. As been mentioned before, you really want to focus on characterizing the asteroid, characterizing the environment, manipulating it, figuring out what the structural characteristics, basically interacting with it. And of course, a lot of these things you could do robotically, but with a human in the loop, you've got an intelligent observer, you can get feedback, you can adjust to unforeseen circumstances, and so it's a lot more efficient to have a human there on the surface, as it were, in the vicinity. We sort of pictured it happening, you'd sort of approach it in a couple of phases. Phase one, you'd approach the near-Earth object, you do a total robotic type of activity, perhaps a survey, so you do some remote sorts of characterizations before you would go down near the surface and try and interact with the surface, take samples, both subsurface and surface, and some of the other characterizations that you've heard about earlier. Targets depend. We asked the question, if you had any choice of any target that you could potentially go to, forget any constraints. For planetary defense, you might want to focus on type S or M. And for science, binary systems, of course, dead comets, and types D, P, and G were the top three, and then there was a prioritized list after that. So there are a lot of synergies between what you might need to find out for science purposes and for planetary defense purposes. And then more along the lines of deep space exploration, this has been mentioned before, this gives you a chance to do mission ops development and operations concepts. There's a lot of different things that you can figure out when you operate far away from planet Earth, out of low Earth orbit, and including understanding the communication delays and how that affects your operations. The onboard autonomy, how do you split up the responsibilities between the crew and the ground, and the strategic and the technical planning and the mission? What kind of emergency response situations do you want to set up and maybe exercise to see if you have a good concept of operations for when you're far away from the planet and you need to consider those contingencies? The teamwork, how you do interact with the ground, and I mentioned the split of responsibilities. It was a recurring theme across all these areas that you really don't want to restrict yourself to any kind of target. The more information you can gather about the broadest variety of targets is a good thing. And so if you're forced to specify, then we would go with the first page, but ideally you want to get a lot of information about any. But really it's not a lot different than what everybody else has come up with, and the team did a great job, and we can all, I think, have a good place to start tomorrow, and we go into our specific areas of discussion. I'll stop there.
I think Barbara said it quite well. We have a huge volume of information, and this is just this is the snowflake on top of the iceberg. So I think in that vein, we have, as you probably noted in all your rooms, we have all the little stickies. We have the roll-ups, the amalgamated products. We're going to be capturing all those, so no fear. We have both the topical outbrief to the group here, and we will capture all the details, and we'll, as we've already said, all the briefings are available online on the website. We've been web streaming, so if you want to recatch or re-review or catch it for the first time, if you happen to miss one, we'll be able to do that. Likewise, we'll have them all archived, and you saw the concept maps. We'll be looking to do that in the future as well, since I think that's another very important communicative tool. So I have a good bit here to touch base. That touches on the data and products. I thought I would, since everybody's been so diligently involved, give you an update on the plane crash. It's a little bit bittersweet. Certainly, what I'd like to report, based upon the information from several sources that we got, is that the former NASA Administrator Sean O'Keefe and his son are alive. They've sustained some major injuries. Understand that they're in relatively stable condition right now. However, Senator Stevens, former Senator Stevens, did pass away in the accident. So that is the latest information that I have for you on that. Of course, this was a time crunch, and I think that is almost the norm, it seems like. But I can assure you that tomorrow we will have more time in each of these activities. But I like the competitive spirit, Chris. You did indeed amp it up at the last moment there, and so we'll have more of that tomorrow. Not like anybody's keeping score, but we'll definitely know who's most prolific tomorrow, and the whole world will as well. We are web streaming this, so bring your A game. But quality, not quantity. No, it's quality and quantity. we're and people, but in that vein. I'd like to also give a big round of applause, and I think it's really fitting for all those folks, and I'd like to name off a couple. So we've had Marguerite Broadwell, Aaron Mahoney, we've had Sasha Sims, and we've had Phil Mongan as just superheroes preparing, but also Derek Wang and Freedom Information Systems, the whole staff, Aries, and of course the Renaissance Mayflower. If we think we're smart by staying at Holiday Inn Express, gosh, what are we going to be by sleeping at the Renaissance Mayflower? So we are setting the bar high for tomorrow. So bring it strong. You're getting a theme here. But in that vein, we have, this has been a rather action-packed, semi-fatiguing activity, but we want to encourage you to. Your reward tonight is we have from 6:30 to 8:30 today at the Museum of Natural History. We have a reception, and we're going to have we're really lucky to have a full viewing of their meteorite collection. And so I think that's going to be a perfect backdrop to this very dynamic and exciting activity. And so we encourage you to proceed once we complete here today to the Museum of Natural History. And our very adept team has given you very detailed, beautiful maps on the metro to get there, or taxis. And we will have some refreshments there as well. And I would finally like to say, check your watches. 5 o'clock, exactly time on target here. So I want everybody to give yourself a huge round of applause. This was a great activity today. Last little cleanup item for those study team leads or facilitators or scribes or recorders. If you could please meet very briefly for 15 minutes immediately after we adjourn. Meet Marguerite Broadwell. We're going to do a little hot wash on today. We can always improve for tomorrow, and so that'll help us tweak it and optimize it. So a very brief 15 minutes or less, just a little hot wash right over in the Business Center, which is immediately diagonal outside the hall. And with that, again, we will start tomorrow promptly at 8 o'clock in the morning, and we have a full and satisfying agenda for you. And at the end of tomorrow, just another final public service announcement, after the close of the normal session at 4:30 for our international, we will have an international roundtable and also an interagency or federal agency session, separate sessions, each following the completion of the normal agenda. So with that, thank you very much, and we'll see you tonight at the reception. Good day.